This STAAR Test tutorial video will be going over exponential functions, specifically how we will use our graphing calculator, our Desmos calculator, to answer a lot of these questions. There will be some math that we have to do that may be unavoidable, but we will try to do as much with the calculator as possible, and more importantly, understand the use of our calculator for all of our exponential function problems. We'll try to do as much minimal math as possible if we can avoid it. However, we can't avoid everything. And with all of this comes an understanding with what we're doing. So we'll try to explain what's going on with everything involving our calculator, involving the steps, with as minimal work as possible. But of course, when we have to show work, we will show our work. The specific calculator we're using is the Desmos graphing calculator, the one that's specifically for Texas, for the state testing in Texas. So here is the website, desmos.com/testing/Texas/graphing. It's all spelled out right here on my screen with the HTTPS : / / I believe that's what it's called. It will look something like this. You'll know you have the right calculator if it says Texas, grade 8, EOC math version. Even though it says grade 8, this is for all your math testing. But that is the calculator we'll be using for all of our STAAR Test tutorial videos. And there is a TI-84 calculator that y'all can use in STAAR testing. However, we're going to be focusing on the Desmos calculator for how easy it is to use, and it's how accessible it is to everybody. So let's get started. Now, of course, during this video, have your paper, pencil, and Desmos calculator out. I would like for y'all to try and do these problems as we go. There's going to be moments in the video where I may ask y'all to pause the video and just think of some things. So at that time, I would like for y'all to write stuff down, enter stuff into your calculator, whatever. And then after you get done with that particular task, play the rest of the video and see what I say about what it is you're supposed to do. Okay. So anyways, let's continue on. So the specific TEKS, the algebra TEKS that we're looking at for this lesson is A.9D. Graph exponential functions that model growth and decay and identify key features, including y-intercepts and asymptote, in a mathematical and real-world problems. So our goals for today. Today I will be graphing exponential functions so that I can, as in you the student, describe and find key features of the graph, and I will know I have it when I can model growth and decay in real-world problems. Some quick things about exponential functions before we go into some exploration with exponentials. So an exponential function is a function of the form y equals a times b to the x power. A, in this case, is a constant. What is a constant? That's just any number in front of the this expression right here. Okay, it could be a 5, could be a 1.3, could be a 7, could be a -3, whatever. A just can't be 0. If A is 0, 0 times anything just swallows it up. So A just can't be 0. B is the base of the exponential function. Okay, the base can be anything that's greater than 0, but it can't be 1. 1 just breaks it down into a different type of problem, so it can be anything except 1. And it has to be greater than 0. There can't be any negatives in the base. X is the exponent, the little number right above the B. The exponent is a real number, meaning that it can be any number at all. It could be a 0, it could be a 1, it could be a -5, 0.3, square root of 2, whatever. It can be any number that's classified as a real number. Okay, and then the typical look of an exponential function is a curve. Think of a table. Think of the corner of the table, except it's more rounded. That is an exponential function. If you hold out an L and you look at the inside of your finger, you see how it curves right here? This is an exponential function. Okay, which is different from a curve from a quadratic function. Okay, quadratics are U-shaped, so they have an up and a down, and then they go back up. Whereas exponentials, they have an up, and they slowly curve downward, and then they just kind of flatten as you continue in one particular direction. Okay, so this is the general view of what an exponential function looks like. Okay, so just some to think about. Look at these two exponential functions. Look at the red line. Look at the base, 1 over 2x. And then look at the blue line, 2 to the x power. What do y'all notice about the blue and red graphs? What do they have in common? What do they not have in common? What do you notice? So pause this video. Take some time to think about some similarities or differences. And after you're done thinking, go ahead and continue. Okay, some things that you may see that they have in common. If you notice right over here, they have the same y-intercept. Okay, this is the y-axis, and this is the x-axis. We notice that they have the same y-intercept of 0, 1. And then 0, 1 is our x, y, the ordered pair that they have in common. X, y, 0, 1. That's the y-intercept. So that's one thing they have in common. Another thing that they may have in common, it may not be obvious, so I put it in Desmos right here. Notice how when you go on the blue line and go to the left, it starts to flatten out at a certain part. Same thing with the red line. As you go to the right, it starts to flatten out at a certain part. That flattened part where it gets close to but never actually goes to it, this is called the horizontal asymptote. How do you spell asymptote? A-S-Y-M-P-T-O-T-E. Asymptote. What is an asymptote? Asymptote is an imaginary line that the graph will get close to but never actually touch. So they have in common a horizontal asymptote, which is a left and right line right here on the x-axis. And we call the asymptote equation y equals 0. So those are some things that they may have in common. We also notice how the red and blue line, they seem to have the same rate of either ascent or descending, descension, whatever. Meaning the same look going up and going down. They both curve at particularly the same rate. Okay, so those are some things that you may notice that they have in common. What are some differences? Well, one of the obvious differences, look at the 2, look at the 1/2. They have different bases, meaning the number right here, because remember our equation, a times b to the x, the b's are different numbers. Now I want y'all to notice with the blue line, we have a whole number greater than 1, where from left to right, it's going in an upwards direction. Whereas the b value for the red line is 1/2. 1/2 is the same as 0.5, which is less than 1, which is making it go in a downwards direction. So those are some differences that we can notice about these two lines. Another thing I want y'all to notice is how the y-intercept 0, 1, they both have the exact same y-intercept. This number right here, whatever the a is responsible for the y-intercept. Notice how there's no number in front of either one of these. They are invisible ones. So they both have a y-intercept in common associated with the number 1. That's why you see that right over here. So that y-intercept is associated with the a value, the invisible number in front of the base. So moving on to the next slide. Here's an example problem of what you may see on the STAAR test. What is the graph of the function f of x equals 6 parentheses 2 divided by 3 close parentheses raised to the x? Select the type of graph and then drag the 2 points and the asymptote, if applicable, to their correct positions. So first off, when you see a problem like this, you need to identify what it is. Okay, if you see the exponent above a little x right above everything else, then we can say that this is an exponential function. Linear is a straight line from left to right. Quadratic are usually U-shaped. Okay, and then linears are usually in the form of y equals ax plus b. Quadratics are usually in the form of y equals ax squared plus bx plus c. So we don't have that. We have neither one of them. Instead, we have y equals a parentheses b to the x power. We have an exponential. Therefore, we're going to graph everything as if it were an exponential function. So now, when you click on the exponential function, we need to have 2 points and the asymptote, if applicable, to their correct positions. Okay, so the asymptote is applied to the exponential function. If we choose exponential, then we have to graph an asymptote somewhere. And we just need 2 points in general. So if you have no clue what we're doing, first thing you could do is take this equation and just plop it into Desmos, which is what we're going to do. F of x is the same thing as saying y, so you can either type in f of x equals, or you can put y equals. You'll get the exact same result. And we're going to type in 6 parentheses, or 6 times, whatever it is you want to put, 2 divided by 3. I'm going to arrow to the right because I want to keep that fraction there, and notice where the cursor is. The cursor ends up being at the bottom, so I'm going to arrow to the right to get the parentheses the same as the other. And then I'm going to hold Shift 6 on the keyboard to get the exponent up here, and then press X. You can also type everything in using a keyboard right here. So you can click on the keyboard, and then you can get to the exponent position by choosing the AB key right there. Parentheses, fraction bars, division signs, whatever. You also have a button for functions right here too. Explore it whenever you get the chance, but we just need to type in this equation right here. So some key things I want y'all to notice is the y-intercept. Notice where the y-intercept is located. If you click on the line, you should see an intercept grayed out dot. That is the intercept for the y-axis, the vertical axis. We need that point, 0, 6. So that's one of the first points you're going to use when answering this type of problem in your STAAR test, 0, 6. So there's one of your points. Let me use a different color. Zero, 6. And then if you can find another good point, good as in whole number point, let's find that. So I'm going to zoom out a bit, see if I can find anything right here. And I see one as 1, 4. What is a good point? It's a point that crosses the corners of these squares. So I see the line crosses right there. And I see another point as 1, 4. Okay, so there's my 2 points, 1, 4. Now the asymptote is usually said as y equals something. Okay, I don't know if you have to graph it using an equation, but the asymptote is basically the line that it never touches. So let's go back to this line right here. Now I want y'all to click and hold and travel along the line to where it starts to flatten out. Okay, now I want y'all to look at the y value which is the number on the right of the comma right here. Notice how it's getting smaller, it's getting smaller, it's getting smaller. 0.054, 0.039, 0.28, and if we continue, 0.01, 0.07, keeps getting smaller, 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 and never actually gets to 0, but it gets very close to it. Now, it can't calculate every single decimal, so it's going to say it is 0 after a certain point, but just know that it never actually touches 0. So if you get far out long enough, that number that it starts to repeat forever, that's actually your asymptote equation. So in this case, it's going to be y equals 0. If we move this up, just for example, plus 3, and we try to go out, notice how it says 3 almost the whole entire time. That is your asymptote equation, y equals 3 in this case. If we had it down to, let's say, minus 3, where it's down here, notice how it says negative 3 all throughout. So our asymptote equation will be y equals negative 3. Since we don't have anything here, it's just 0. So y equals 0 is our asymptote equation. That will be a horizontal line, imaginary dotted line, that the equation will never touch. So your line should look something like this when you draw it out. Okay, so that's how we do a problem like this. For this next problem, we're going to be graphing more equations, more exponential equations, and we're going to look at a problem where we need to find the correct graph. So just like what we did with this previous problem right here, we're going to use our Desmos calculator to type the equation in, and then we're going to use our tools to make sure that everything matches. We're going to use what we know about exponential functions and try to match it with the following question that's fixing to come up. Okay, so for this problem, which graph best represents f of x equals 5 parentheses 3 to the x power? So we're going to type this into Desmos and then figure out which one matches that graph. So if you would like, go ahead and do that on your own. Otherwise, I'm going to continue and show y'all how to do this. Okay, so again, type this into Desmos exactly as you see it. Y equals 5 parentheses 3 close parentheses raised to the x power. Okay, and if you need to zoom out on your graph, make sure you get the line and get most of the features there. And we're trying to match which of these 3 graphs looks like our original. Okay, well, they all look like our original equation from up top. So what do? Well, let's zoom in on the key features. One of them being the y-intercept, where it crosses on the y-axis. So we're going to look at that point. You can click on the line and you should see that gray dot on the y-axis. You can either zoom in or just arrow or hover over that dot and it'll give you the y-intercept, which is 0, 5. So that's our first thing that we're going to check with all of these is the y-intercept. Notice that B, let me highlight right here, B and C have the same y-intercept, but A does not. They do not have 0, 5 in common. So A is no bueno. Now, next thing we notice, they both have the same x asymptote. They both kind of even out to y equals 0, as does our graph right here. They both kind of get to where y equals 0 is our asymptote. So we need to find something else that they may have in common. Well, let's look for some points. Let's look for some nice points, whole number points. And I see a couple here. I see 1 for letter B at 0, not 0, 1 comma 15 as one of those points, and I see another nice point for letter C at 1 comma 10. So there's a difference between those two. Let's see which one has that point in common. So let's go back. Let's zoom out on our graph, and then let's go to 1. You could do that by just click and holding on the line, and then just moving until the x value gets to 1. And then if you want like an exact point, you can zoom in so that it'll try and get an exact point. And we have 1 comma 15 on this equation. So let's go back. Which equation, which graph has 1 comma 15? Letter B. Therefore, C and A are not our answers. B is our answer. Again, this is what we use. This is how we look through using Desmos to see which one matches, knowing these different properties of exponential equations. Anyways, letter B is our answer. Okay, now I'm going to show y'all how to use tables and how to create functions, create exponential functions using Desmos. Because, well, let's look at this problem right here. The new houses are being built in a neighborhood. The table shows the exponential change in the number of houses in the neighborhood over this last 6 years. Notice how it says exponential change. So we're gearing up for an exponential related problem. So which exponential function best models the data? Then look at our answers. We have exponential functions that are being displayed. We want to know from this table which one best represents our table. So there's two ways to go about this, but I'm going to teach y'all the first main way because it's very important, is how to create exponential functions using Desmos. Okay, and we're going to be using the equation I just highlighted right there. Y1 squiggly or tilde, I think, T-I-L-D-E. I think that's what the squiggly is called, but I'm just going to call it squiggly. A parentheses, B close parentheses, X1. So we're going to be using that to create a exponential model based on the table that we type in. Okay, this is not going to be given to y'all. This is something that you may have to memorize or may need to know how to type into Desmos. So pay close attention to this equation. So what we're going to do is, to find the best model, we're going to plug all this this data into Desmos by creating a table in Desmos. So whatever you have in your equations, make sure they're deleted. And for wherever you have this, preferably on the first line, you're going to click the plus button and then click the table option. It's going to give you XY table. If you want to mess with some of the settings, you can click and hold the dots right here. It'll give you some more options on the type of points it creates. The opacity, meaning like whether it's a solid line or if it's has some whether it's variably see-through is what I was trying to say. You also have like how thick the line is, how thick the points are going to be. You also have like how the different colors you can set it to, whether the dots will connect or not, the type of lines you want these you want the line to create, whether it's dashed, dotted, whatever. And again, opacity and how thick the lines are. Whether you can drag certain dots, certain things about it. I haven't really messed with that particular option, so I don't know what it does. We may explore it later, but we'll see. But this is the main thing we want. We just wanted to create some dots, and that's it. So now we're going to enter everything that we see on this table for the x values onto the left side of the table, for the y values on the right side of the table. So I'm going to put 1, 2, and then 3, and then if you hit enter, if it notices a pattern, it'll auto-complete the table. So I see that it checks out. I'm just going to hit enter, enter, and then just leave it right there for 6. For the right side, there may not be a pattern, so just make sure you get all the values there exactly as it should be. 27, 35, 45, 68, 93, and 124. Okay, now if you go to the right, you may have to zoom out a little bit, but you should see your dots right there. Okay, if you click on this, just click instead of hold, it'll turn those dots off and on. Okay, and there we go. Now on the next line is where we're going to build our equation. That equation that I have right here, we're going to type it in exactly as we see it. y1, and then to get the squiggly, you can use your keyboard around here to find those different things. You may have to type or may have to click around to figure out where they're at. I see it right here. Or on your keyboard, if you're looking at your keyboard, if you're looking at your keyboard, right next to the 1 key should be a little comma, apostrophe, or whatever, and that little tilde squiggly thing. So you just got to hold shift and then hit that comma button right next to the 1, and you'll get the squiggly. And then enter the following as we see it. Excuse me. A parentheses B close parentheses, and then get to the exponent position. You're going to hold shift, press 6, or you can choose the AB button right here to get to the exponent section, and then type in x1. Okay, we don't need log mode for the moment, or maybe we do. No, we don't need log mode for the moment. So then here we go. Or actually, yes. I'm sorry. Click log mode in order to get more accurate numbers. Okay. Now it'll create a model based on what you have right here, your x1 and your y1. That's why we type y1 and x1, so that it'll pull from the table that you created right above it. Okay, we don't need r squared or r at the moment, so we're going to disregard that. That's for something else in statistics, or in a more statistical problem that we may need. Right now, we need to look at the parameters, the a and the b. Okay, these 18.9 for the a and 1.3 for the b are what create this equation right here. So it's saying a is 18.9. I'm going to put on my paper 18.9 is a. And then for the b we said was about 1.36, so it could be, if we rounded to one decimal place, 1.4. 1.4. So b is 1.4. And then we have the little x right here. Again, a and b are being modeled as 18.9 and 1.3 based on the equation that we just put. Well, which of these letters, or which of these answers models this graph or this table right here? The only one that models it is C. 18.9 parentheses 1.4 raised to the x power. And that's our answer. Now what we could have done is we also could have just put this table, put the table in, like we did right here. And we could have also typed each equation to see which one best matched those points. 1 point y equals 1.4 parentheses 18.9 close parentheses raised to the x power. This is letter A. I'm looking to see if letter A matches these dots, and they don't. They're not close to all the dots. And I would just brute force my way into seeing which one best matches. Now the issue with that is, notice how from our previous answer, y1 squiggly a parentheses b raised to the x1. Whoops. Notice from our previous answer how they have decimals, and these don't include all the decimals in the problem. So I would be very wary of just brute forcing your way for this, because some of them may end up being close and you'll have to pay extra close attention. This way, the way that we just did this, will at least model it as closely as possible without having to do all that guesswork. Okay, so that's it for this problem. Letter C is our answer. Quick refresher before we get on to the next question here. So again, exponential equations, exponential functions, graphs, their key features. That's what we're exploring in this lesson. A parentheses b close parentheses to the x, or a times b to the x, same thing. The a value is essentially where you start, where your y-intercept is. Okay, that's your quote-unquote starting value for most scenarios. Excuse me. The b value, the base, is the ratio of either growth or decay. We didn't mention this before, but if you've been noticing some things, any number where the base is bigger than 1, we notice that there is an increase. We call that growth. That is exponential growth that is happening. Any number that's between 0 and 1, meaning like 0.2, 1 half, 3/4, 0.76, 0.0059, all of those types of numbers, anything between 0 and 1 is considered decay. That is exponential decay, a decrease that is happening. Now, unless otherwise noted, the asymptote, that imaginary line we've been talking about, the line where it just kind of flattens out and never actually touches, that asymptote is a horizontal line, an imaginary horizontal line, and the equation, again, unless otherwise noted, is y equals 0. That equation will change if you have something being added or subtracted at the end of everything. So for example, if we have +3 at the end, well, now the asymptote is now y equals 3. If we had -7 at the end instead, well, now that asymptote is now y equals -7. So unless otherwise noted, the asymptote is always going to be y equals 0. Okay, so we're going through these equations, these exponential functions equations, whatever, and we're trying to identify key features and then also how to build these equations from tables that are given to us. So we're trying to look through and identify things from that equation. So with that in mind, let's look at another STAAR test problem that you may see. Which statement about the graph of the function f of x equals 35 parentheses 1.4 close parentheses to the x is true? And then we're given 4 different things. Okay, so it talks about the y-intercept, the x-intercept, whether it's increasing or decreasing, and the asymptote of the function. So we can do all of this without a calculator. However, it's probably best to look at it and then identify things from here. So what we're going to do is we're going to get Desmos again, and we're going to graph that function. Whatever you have in your Desmos calculator, just erase it, and then we're going to enter the following. You can enter this as y equals or f of x, doesn't matter. This time I will use f of x just to show y'all. So f of x is equal to 35 parentheses 1.4 close parentheses raised to the x power. Now, a few things. Without even looking at the graph, I can notice that this is a number, the base, the b value, is bigger than 1. So I know there's going to be a growth happening. I know that the starting position from the a value is going to be 0, 35. Unless there's something that's being added or subtracted from the end, that number is always going to be the y-intercept, okay, the start, 0, 35. I don't know about the x value. I don't know. I do know that the horizontal asymptote should be y equals 0 because there's nothing being added or subtracted at the end. So all those things I know by just looking at the equation right here and knowing its properties. But let's say you don't know. Well, let's just graph it using our calculator and take a look. So again, by graphing it, we notice that from left to right, again, we read graphs from left to right, we notice that there's an increase in values as we keep on moving through the graph. So there's a general increase, exponential growth happening with this function. The y-intercept, when you click on the line, is that dot right there, okay, where it crosses the y-axis. You could click on the dot for it to just show right there. 0, 35, that's the starting position, the y-intercept. We know also that the horizontal asymptote, as we click and drag this point all the way to the left, notice how it goes to 0. Remember, this is a line that it never touches, so it's never going to actually reach 0. It's just constantly hovering over that line, but never actually touches it. So the horizontal asymptote is y equals 0. All right, now because it's never going to actually touch 0, it's never going to touch that x-axis, meaning there is no x-intercept. So with all of that in mind that we just explored on our graph, let's look at the problem again. The y-intercept of the function is 0, 35. Is this true? Yes or no? So far, yes. This is true. So I'm going to put a dot to represent this is a possibility. X-intercept of the function is 1.40. We just talked about how it doesn't actually cross the x-axis. So B is not for consideration. The graph of the function is decreasing. No, because we just saw for every value from left to right, it is continuously increasing. So C is no good. The asymptote of the function is 0.4. No, not true either. Because again, if you don't see anything, it's understood that the asymptote is y equals 0. So the only one that makes sense is letter A. The y-intercept of the function is 0, 35. Okay, now talking more specifically about exponential growth and decay, there are formulas associated with either one. Okay, let's take a look. So notice how this is still in the form of a parentheses b raised to the x power. So they still have an exponential form. However, sometimes we may want to find out what the b value is. Now, b value is usually a percentage of either growth or decay. Sometimes things grow at 50% more every so often, or 75% less so often. Okay, 100% is the total. If something grows 50% more, then it's the growth in general will be 150%. I'm just adding those two together. Okay, so again, 1 is normal. If things are growing at 50% or 0.5, then that general growth formula will have a 1.5 in the middle. Let's say things are decreasing by 75% or by 0.75 in decimal form. That will mean that things are decaying, so we have to subtract from the normal 1, from 100%. So 1 minus 0.75 means there's a 0.25 decay rate happening. Okay, something to keep in mind. This may be something that you have to memorize. I didn't see this in the Algebra 1 STAAR formula chart or formula sheet, so this may be something you have to keep in mind when creating exponential growth or decay type problems. Okay, and again, exponential growth means things are moving up. Exponential decay from left to right to mean things are going down. So let's look at an example to kind of familiarize ourselves with writing these formulas. So Joe, in this example, Joe drank a cup of coffee that contained 120 milligrams of caffeine. The caffeine is eliminated from the body, so eliminated at a rate of 9% per hour. We want to write an exponential function to model the amount of caffeine remaining in Joe's system after X hours. So we're trying to create an equation based on the growth or decay of this problem. So we're, in a sense, trying to find out the A times B to the X power. Now this B, however, is determined by whether there is a growth or a decay. So we need to look at some of the wordage of the word problem here. There's a word that I underlined that gives a hint as to whether there is growth or decay happening. So if you look at the second sentence, the caffeine is eliminated. What does eliminating mean? It means getting rid of, essentially, in layman's terms. So I'm getting rid of this caffeine from the body at a rate of 9% per hour. So this tells me that decay is happening. So I know that I'm going to use the formula A parentheses 1 minus R, close parentheses, to the X power. A, from what we talked about before, is our starting value. How much we have at 0. 0 usually being time or a certain measurement at the start of something. So at the start of this problem, not that one, at the start of this problem, he's going to drink a cup of coffee and he's going to have 120 milligrams at the beginning. Okay, so the initial value is 120 milligrams. Now we need to write the rate. The rate is 9% per hour. We need to turn that into a decimal. If you forgot how to turn decimals into, percentages into decimals, there's two ways. One of those ways is taking 9% and then moving its current decimal place to the left twice. And then any gaps that you see, fill in with zeros. So we have 0.09 as a decimal. Okay. Now, the other way is by using a calculator and dividing by 100. So take 9%, the whole number, divide by 100, and then you will get its decimal form, 0.09. 0.09. We're going to use that for the R value, 1 minus 0.09 to the X power. And then we're just going to do the math real quick. 1 minus 0.09, which will give us 0.91. So this is 120.91 to the X power. If you want, you could put Y equals, you could put F of X. Whatever the problem has, that's what you put. And that's how we create this function, this exponential model of Joe drinking a cup of coffee and having it eliminated from his body after a certain amount of time. Okay, so we have a function right here. The function P of X, the P doesn't matter in this case. It's the same thing as Y equals. P of x, f of x, h of x, whatever. P of x equals 834 parentheses 1.1 close parentheses to the x gives the number of bald eagles x years after they were added to the endangered species list. Each student attempted to interpret the model. So we have 4 different students. I want you to read those interpretations and see if they make sense based off what we just learned from everything about exponential functions. Try to see if their interpretation makes sense. So if you would like, go ahead, pause the video, see if you can figure it out. Otherwise, I'm going to continue on and explain what each of these means. But I would like y'all to attempt this first. So Anna says there were 834 bald eagles when they were added to the endangered species list. Well, let's look at where the 834 is here on the function. 834 is our A value, which is our starting position, where they start. So we can safely say that 834 is how much they start with. In this case, the number of bald eagles that they start after X years. In this case, 0. So they were 834 bald eagles when they were added to the endangered species list. True. For right now, this is true. Ava, the number of eagles decreased each year by 11%. Well, let's look at the inside right here. This is talking, so this was talking about the A value. This is now talking about the B value. Because remember, our exponential equation is A times B to the X value. A is the constant, B is the base. So we're talking about the base. Number of eagles decreased each year by 11%. Well, if this were decreasing, that B value would be less than 1. Would be bigger than 0, but less than 1. So it would essentially be something like 0.9, 0.8, 0.7, 3 halves, or I'm sorry, 3 quarters, 5 sixths, 0.0059, those types of numbers. But we don't have a number that's less than 1. We have a number that's bigger than 1. So this would not indicate decrease. This would indicate growth instead. And if you are not sure, let's graph it. So let's type this into Desmos. Y equals 834 parentheses 1.1 close parentheses raised to the X value. And as you can clearly see, the graph is going up from left to right. So there's no decrease happening from this model. Okay, the asymptote for the function is y equals 1.1. Is that true? Well, let's say we don't have any clue what anything from the equation is telling us. Let's just look at the graph. So the asymptote is that imaginary line that the graph will never touch as it continues one direction. So in this case, going to the left. As we go to the left, notice how it's getting smaller and smaller and smaller, but it's never going to actually touch that line. 0.4, and it just keeps on going all the way to the left. 0.00003, 2, and so on. So it's never going to actually touch a certain number. And if we don't see that number on the outside of it, we can assume that the asymptote is y equals 0. Therefore, Alan is wrong. Ava was wrong, Alan was wrong. Andrew, the number of eagles increased by each year by 10%. So, is there an increase happening? Yeah, there's an increase. Now, do we know if it's 10%? Well, let's figure that out. That inside, that parentheses part, the B value, since this is growth, is 1 plus R. Well, what is that R value? So 1 plus what will give me 1.1? 1 plus 0.1. This is our percentage. What is it as, so what is this decimal as a percent? Well, to get the percent, we could take 0.1, move the decimal to the right twice, fill in any zeros, and then add a percent, and this will be 10%. Or you can take 0.1 and then multiply by 100, and you will get your percentage, which is 10%. Just like we did with percent to decimal, let's say we want to go from 10 to decimal, we divide by 100, we get 0.1. To go from decimal to percent, you multiply right here. So Andrew is correct that the number of eagles increased each year by 10%. So Anna and Andrew are both correct. Ava and Alan are not. So now, read this problem and ask yourselves, well, as you're reading this problem, you want you to ask yourself, how do you know from the question stem, which part of the question will tell you whether it represents growth or decay? So read the problem, figure it out. Otherwise, I'm going to continue on. So try this on your own, please. Okay, so a shipping company started with 40 employees. The number of employees at the shipping company increases at a rate of 7.5% each year. Which function can be used to model the number of employees, f of x, at the shipping company after x years? Which part of this question tells me whether this is a growth or decay type problem? Right here. Increases. Increases tells me that this is going to be a growth, exponential growth. Or at least a growth in general, okay? But when you look at the problem, when you look at each of the question, we now see, oh, this is exponential growth. All right, so now which one of these can model the scenario that we have at the front? Well, the company started with 40 employees. Exponential equations are in the form of a times b to the x. A is our starting position. So each of these a's need to be what number according to our word problem? 40. They need to be 40 employees. They started with 40 employees. So which two answers can we mark off automatically? A and C, because they both have 43 and we don't want that. So now here's the next part. It is increasing at a rate of 7.5% each year. Increase means with our exponential function, they need to be bigger than 1. If it's smaller than 1, it is a decrease. So without even having to graph this, or there's no graphing involved, it's mostly understanding what each of these numbers are doing to the exponential equation. B or D would be our answers here, but notice their B values. We have increase, so which one of those would be our answer? Or which one of those can we eliminate based on the fact that this is an exponential growth? Excuse me, D. Because look at the decimal on the inside. That is 0.075. That is a number that's less than 1, which would indicate decrease, decay. 1.075 would indicate growth. So B is our final answer. So let's say you just wanted to create the equation. We know that 40 is there for sure. And since this is growth, we know that we're going to have 1 plus R. What is R? Well, R is the percentage. But we need to take 7.5%, change it to its decimal form. So either divide it by 100 or move the decimal point to the left twice. And we get 0.075. So 1 plus 0.075. Y'all could type that into the calculators. We should get 40 parentheses 1.075 close parentheses raised to the x. And the only answer that fits that model is letter B. Okay, another type of problem, except this is a drop-down, fill-in-the-blank type of problem. So let's go through it. It's structured very, very similar to what we just did, except now we need to choose from a drop-down menu, which is something similar to what you're going to experience in the STAAR test. Laboratory technicians recorded a if you would like, by the way, if you want to try to figure this out on your own, go ahead, pause the video, and see if you can figure out which of these we're going to be circling for each of these blanks. So we'll call this number 1. We'll call this number 2. And then we'll call this number 3. So what are we going to be filling out for each of these boxes? If you would like, go ahead and pause the video, see if you can figure it out on your own. Otherwise, I'm just going to continue on and show y'all what to do. Okay, laboratory technicians recorded a population of a species of bacteria each hour for 7 hours. The population in thousands after X hours can be modeled by the exponential function 575 parentheses 1 plus 0.40 close parentheses to the x power. Choose the correct answer from each of the drop-down menus from these statements. The initial population of the bacteria when the technicians began recording was what? So look at this number. Where is our starting position? What is the initial, the starting position? Initial means starting population. So our starting population, our start, is the first number we see here, the A value. So we have 575. We don't see it right here except for this, but notice how it says the population in thousands. So 575 is actually in thousands. Now, look at the inside. For increase or decrease, and the population is which one? Well, look at the inside. We have 1 plus something. Okay, 1 plus 0.40, or if it's a number bigger than 1, like 1.4, we will know that this is increasing. The population is increasing. But what is the rate? Well, that rate is the R value that's right here, 0.40, but that's in decimal form. I mean, you can probably guess what this is going to be, but the rate should be 40%. However, let's say you don't know what it is. Well, the rate is just the number that's added to the 1, the 0.40. So, to change that into its to its percentage form, you take 0.40, either multiply by 100, or move the decimal point to the right twice for the shortcut. And either way, the percentage rate is 40%. Okay, so here's another type of problem where you actually have to create the equation yourself. Again, if you would like, go ahead and try to pause the video and try this problem on your own based off of what we just learned. Otherwise, I'm just going to show you what this is. But again, try this on your own. The only thing that I'm going to give y'all is that our equation is in the form of a times b to the x, and it's either going to have one of the following. A1 plus r to the x, or A1 minus r to the x. Again, we got all this information based on the slides that we did earlier. So try this problem on your own. And then after you're done, unpause the video and then see what I say for your answer. A sample substance with an initial mass of 963 grams is decaying at a rate of 27% per hour. Create a function that can be used to find y, the mass of the substance, in grams remaining after x hours. Enter your answer in the space provided. So decaying gives you a clue. Decay means that there's an exponential equation that you're going to have to create. And then more importantly, you're going to use the minus version of the 1 minus r part of the decay formula. So, first off, we need to know what the initial mass is. It says find y. The y is our equation, so this is going to be y equals something. We know we're going to start with our a value. 963 is our A value, so that's going to be 963. Our parentheses is going to be 1 minus whatever the decimal of our rate of decay is. So 27% as a decimal, I'm going to do it right here. Move the decimal point to the left twice or divide by 100, either way. And our decimal version of the percent is 0.27. Okay, so we're going to have in our parentheses 1 minus 0.27. This is a number that we can actually simplify, so we're going to go ahead and do that. So 1 minus 0.27 will be 0.73. So I don't know which one it'll accept, to be honest. Both may be correct, but either you can just do 1 minus 0.27 and then put the x on it, or you're going to have to type in 0.73, close parentheses, raised to the x value. Both are technically correct, so you can either write it like this first way, or you may be able to write it this way: y equals 963, parentheses, 1 minus 0.27, close parentheses, raised to the x. The first way is the nice, cleaner way. The second way is not so nice because of the parentheses, but it's still the exact same answer. And that's it. So that's it for our STAAR test review over exponential functions. If you have any questions, make sure you let me know if I'm your teacher, or you let your teacher know in general. And I'll see you in the next video.